Our next speaker is an engineer, product designer, and all-around electron gunslinger. He lives in rural Virginia, where he hosts a refuge for misfit electronics and surplus scientific equipment. Do you know how to make tubes? Stick tight, you will. Please join me in welcoming to the Hackaday Supercon stage, Nick Poole.
Thank you for the generous introduction. Yeah, I'm Nick, and today I want to talk about building vacuum tubes in the home lab. It's a huge topic, so we're not going to be able to get really into the weeds on the technical end as badly as I really want to do that. But what I mainly want to do is leave you with the impression that if this is something that is at all interesting to you, that you can do it. It's one of those things that sounds crazy at first, and for sure there are some gotchas involved, but like building anything else, you can solve these problems one at a time. So before we get into any technical stuff whatsoever, I want to talk a little bit about how I ended up here, because earlier this year I had no experience building vacuum tubes. I wasn't even that familiar with how vacuum tubes worked. And so in February, I stumbled across a YouTube channel. One of the things that I do with the precious little time I have on Earth is hunch over my computer and watch hours and hours of YouTube. And I found this channel called Usagi Electric. It's this guy, David, in Texas. It's kind of a retro computing channel, but he got the tube bug, and he started building a computer out of vacuum tubes, out of vacuum pentodes. He's building a 1-bit computer, sort of inspired by the Motorola MC14500. And I started looking at how many tubes were involved in this thing, and it's hundreds. And I started thinking, can you put all of these tubes in one? I understand why they're separate tubes, because you don't want one element to go out and have to replace the whole computer. That makes sense to me. But if you wanted to, just as a fun idea, could you put them all in one vacuum tube? Could you take all of the elements from these individual little glass bulbs and put them in one chamber and pump it down and have it still work? And so I tweeted basically that. I was like, can you make like a 555 vacuum tube? And people got back to me and they said, yeah, people have kind of attempted that. There was something called a compactron that is basically a vacuum tube with a couple different types of vacuum elements in it. There were things as crazy as this 256-byte memory tube. That is a lot of memory in a single vacuum tube, and that vacuum tube, I believe, is like, the size of a tall beer can. Not a small vacuum tube. And then there are things like the Korg new tube, which is this. If you haven't seen this, this is really interesting. So Korg teamed up with Noritake, who is the company that makes like vacuum fluorescent displays like you find in like a car stereo head unit. And they built a VFD specifically with a very large anode surface area that can be used in audio amplifier. So it is specifically made as an amplifier tube, but it's built with this sort of laminated glass flat envelope that you're used to seeing on a vacuum fluorescent display. And so all of those things were pretty similar to what I was imagining, but they weren't exactly what I was imagining. And so at the time, I had been doing some renderings in Fusion 360 for my day job at SparkFun Electronics. And so I was getting pretty familiar with that software, with that workflow, and I wanted something to work on that wasn't work. I wanted like a fun art project. And so I decided I was going to do some art about vacuum tubes. And I was inspired by Nanoraptor on Twitter. I said, I'm wasting my time pulling a Nanoraptor about this. If you're not familiar with Nanoraptor, she is an artist who makes these, I think, sort of equally charming and also horribly cursed photoshops of technology such as this triangular USB connector that, of course, was discontinued because users found that they would have to rotate it up to 6 times before being able to plug it in. Or the Macintosh Apple Display L, which was a compromise between the portrait and landscape style monitors. The L, of course, stands for laser disc. And so I started doing that. So I started putting together these renders. And these were some of the first things that I did. And they were completely unmoored from any sort of reality or physics or material science. It was just, what does this thing look like in my imagination? And I started publishing these on Twitter and just giving them names. I created this fictional company called Integrated Thermionic that made integrated circuits, but in vacuum tubes. And things only got weirder from there because I just sort of started doing this concept art, very sci-fi concept art of these glass and steel sort of assemblies that felt like an alternate history version of some of the things that we have now. My prompt here was like, what if it had taken us too long to figure out semiconductor, and we just had to miniaturize and integrate vacuum tube technology as much as we could to still get to sort of the modern information age? And so from there, I started to simplify, and I just wanted to make some really pretty VFDs. VFDs are vacuum fluorescent displays, and these are just a couple of things that I put together to post on the internet just as art. You know, these aren't really concepts for tubes, although these are much more grounded in the way that VFDs are actually built. These are devices that could theoretically be functional. And then I started really thinking about Integrated Thermionic as an art project, like an alternate history project. It was world building. And I started coming up with packaging for this company that would have existed to go along with all of these products. And then, as long as you're thinking alternate history, I mean, we have surface mount components now. Why wouldn't we have surface mount vacuum tubes? So we have some carrier tape here with miniaturized vacuum triodes. We have some cold cathode gas tubes instead of LEDs. That would make the batteries on your badges a lot bigger. And I even started thinking, you know, integrated thermionic, it would be it would be beholden to all of the same trends in graphic design that everyone else was. So, you know, if you imagine they started up in the 40s through the 50s, you would have this vibe going on. Things would loosen up and get a little bit more hip in the 60s through maybe the 80s. It's getting a little stale, and then all the way over to the early 2000s, they're starting to look a lot like Radio Shack. And Tube Time on Twitter called me the nanoraptor of vacuum tubes. Mission accomplished. Ugh. Remember? Never mind. So I started a little Patreon because I had this goal that I was going to make all of these renderings, and then I was going to put them all together into like a coffee table book. I wanted to publish a book that was a catalog for this company and had like fake data sheets and like marketing copy, and then of course all of these really pretty renderings. And I was running out of reference material. At this point I'm thinking I need to make enough of these renders to fill a book. And I am looking at the same like 12 tubes on Google image searches. So I dig into my stash and I find that I have put away this little bundle of miniature vacuum tubes that I got off the free table at work years ago. And I put them away. I said, oh, these are cool looking. Don't know what to do with them. I'm going to put them in a box. And I pulled them out of the box, started looking at them, and they were cool. But if you look here, there's like 6 different tubes here. It's just a lot of the same tube. And so I went on eBay to see what I could see. And it turns out no one's going to stop you from just buying tubes. You can just buy a bunch of tubes. So radio shops are closing down all the time, all CB radio shops and hi-fi repair places, and they just box up all these tubes and they sell them as a lot. They come out to about 50 cents a tube, which is a really good deal, I guess. I'm not using them for anything, so is it a good deal? So I bought more of them. And I bought more of them. And now it's a horde. This is a collection I've started now. That's my hobby, is collecting vacuum tubes. And at the same time, I had a little bit of a viral moment. I mean, it's not viral in bigger Twitter terms, but it's definitely viral in tech Twitter terms. A lot of people were really into this miniature CRT display that I did. And I got a lot of replies from people either wishing or assuming that it existed. And I started thinking, like, it could exist, right? Someone could build that. I could maybe build that. And I got a few tweets from people who knew better than me about CRTs saying, you couldn't really build it that way. And I thought, I know I can't build it that way, but I can, come on, I can build it. And the more pushback I got from people telling me how hard it was going to be, the more inspired I was to build something. And so I started taking my renderings and tearing them down, and I started really thinking about, like, physically, how would these things be manufactured? I started reading reference materials from the middle of the century about how these things were actually made. I was watching videos that were these old, beautiful industrial films by the companies that were building vacuum tubes in the thousands, tens of thousands, hundreds of thousands. They loved to show off their production line and every step of the process because it was, like, very modern and impressive. And so I started sort of copying what I was seeing and trying to extend it to some degree. And then I found out other people are doing this. So if you go on YouTube and you look up, like, DIY vacuum tube, make a vacuum tube at home, homemade vacuum tube, right? You find this guy, Ron Soyland, Glasslinger on YouTube, and he makes reproduction vacuum tubes for radios, to refurbish old console radios. But he also does all sorts of other weird stuff. I watched him replace the bearings in a turbomolecular vacuum pump with skateboard bearings. They happen to be the same size. He swears if you pull the seals off of them and dunk them in solvent to get rid of the grease, that they work just as well. I don't know if I would bet my turbo pump on it, but he was happy to. On sort of the other end of the spectrum, there's Dalibor Farney. Now, he is one of, I think, 2 people in the world who are currently making brand new Nixie tubes that are commercially available. You can go buy Nixie tubes from this guy. And he makes them in a factory in a castle in Czechia. And he started not knowing anything about vacuum tubes in 2011. You can go find his personal blog where he has some early success building a vacuum tube, and now he is a company. And has a beautifully appointed lab with top-of-the-line equipment, a lot of which he has either built or modified to purpose. And then sort of back to the garage, we've got JD Flyback, who does absolutely remarkable work with just the bare minimal tools. He's building triodes and CRTs using basically a propane blowtorch, a power drill as a glass-blowing lathe, and a little homemade, all of his power supplies and everything. His transconductance meter is in a cigar box. It's great. It's real hacker stuff, and it's very inspiring. And of course, there are others on YouTube as well. A lot of people want to build X-ray tubes. And so they're the Science Furry, Atomic, they're doing X-ray stuff. We've got an incredible video of Claude Payard building sort of artisanal vacuum tubes for radios, and then this great video from the Ottawa Vintage Radio Club. So I decided to throw my hat over the fence and buy a piece of equipment. I bought an ion gauge. And an ion gauge on its own isn't all that useful, but it is the piece of equipment that you need. It's the sensor head of the gauge that you need to measure the high vacuum that you need to create inside of a vacuum tube for it to work correctly. And once I put my money where my mouth was, the community showed up. So there's a lot of, I don't want to call it gatekeeping, but I think people get disappointed when newbies show up and they say, I'm going to make a vacuum tube. And they go, okay, here's all the stuff you need. And then they never hear from them again, because they go and they research and they find out it's hard to do. But as soon as you buy something and you tweet about it and you say, hey, I'm going to try to build a vacuum system and I just bought some stuff, then people start messaging you with all sorts of helpful advice. They start sending you hardware. They invite you to the cool kids Discord where they talk about homemade fusers, stuff like that. So before we go much farther, we should probably talk a little bit about how vacuum tubes actually work. This is sort of a model of the simplest tube that you can have. It's a diode. Diode, we know diodes in our day-to-day life, right? They only let current flow in one direction. The reason it's called a diode is because it has two electrodes, diode. And in a vacuum tube, the simplest type of diode is directly heated. So you have a filament on one side, and you have an anode on the other side, and that's just a plate of metal. And what you do is you heat up that filament, and we do that by driving a current through it. It's just a resistive heater. There's no magic about the current going through the filament. If you could heat the filament a different way, it would still work. If you heat up the filament with focused sunlight or a campfire, it would still work. But electricity is the easiest way. So we do that. What happens is that we know, I'm not going to get too into the physics of it, the particle physics. Frankly, I don't understand it. But I will say that, in a metal, we have, if we think about sort of the free electron model, in the metal of the filament, we have lots of mobile electrons, and they're not all going to have the same energy level. Some of them are going to have higher energy levels than others, and if we raise the mean energy level of that piece of metal by heating it up, all of that thermal energy will cause some of those electrons to overcome what's called the work function of the metal. And the work function is basically the amount of energy that is required for the electron to leave the surface of the metal and enter a point in the vacuum outside the metal, basically really far on an atomic scale, but still close enough to the surface and it's not really affected by a field outside of it. So it's far enough to get launched off of the surface of the metal and not get sucked back onto it. And there are things we can do to lower the work function of metals, and we can talk about that later, but mostly what you need to know is that you heat this thing up and it starts boiling off electrons. That's something that people say, it boils off the electrons. And that's called thermionic emission. So the cool thing about that is, if this is ejecting electrons and you set up a circuit between the anode and the cathode, and you have a battery connected to that circuit, charges are going to build up on this side, and then they will be ejected by thermionic emission and create space for new charges here. And so you create a current flow across the tube, which isn't all that special except if you consider the reverse case, which is that if you turn that battery around and you try to get current to flow the other direction, the anode isn't hot. So there's no thermionic emission to actually get those electrodes to leave and head back to the cathode. So now we have current flowing in only one direction, it's a diode. That can complicate the way that you build your circuit if it's directly heated, because now you have a potential across the filament to light it up, and you have a separate potential across the tube. So what we ended up doing was creating something called an indirectly heated diode, which is where you take the filament and you separate it from the cathode. So electrically, they're insulated from one another, but the cathode can be heated by the filament. And you can just keep doing this. You can add a control grid. Now you've got a triode. Triodes are interesting because if this control grid has a positive charge relative to the cathode, then any electrons that boil off of the cathode are going to get accelerated towards the control grid and smack into the anode. But if it has a negative charge, they'll get repelled by the control grid, and they'll eventually fall back onto the filament. Or they'll attach and sort of like, they'll dissipate through some way through the tube. But they won't hit the anode, you won't get current flow. And you can sort of adjust how much current flow you're getting by changing how much charge is on the control grid. And if that sounds familiar, it's like a transistor. That's an amplifier, baby. So we can build audio amplifiers, we can build operational amplifiers, build all sorts of things now that you have this sort of valve, right? And you just keep on adding grids. So it turns out there's a problem with triodes, which is that if you're accelerating the electron hard enough, it can hit the anode, and then you get secondary emission from the anode, and electrons pop off of it, and they gather on the screen grid itself, and then the grid gets charged up. You don't want that to happen, and so you throw another grid in there, right? And that grid is at the same potential as the filament so that it slows down the electron by the time it hits the anode, and then that causes other problems, so you keep adding more grids. Eventually, you end up with the most stable thing, more or less, which is a pentode. But there are other ways to solve that problem. We created something called a beam tetrode, which uses these sort of like arms that wrap around to sort of electrostatically steer the electron beam towards the target. VFDs are basically triodes, except that the anode has some phosphor on it that glows. CRTs aren't all that different from all of this. The electron gun in a CRT is not dissimilar from the filament and cathode arrangement in any other vacuum tube. And you can put multiple elements in the same tube. There were a lot of dual tetrodes. There were a lot of dual pentode diodes. There were a lot of, multi-element tubes built. So now that we understand a little bit about how vacuum tubes work, I want to talk about some of the materials that you will need if you want to build a vacuum tube. Some of these things you don't actually need. I thought you needed them, and I went looking for them, and they were very hard to find. And I solved the problem of finding them, only to find out that I didn't really need them. But it's not a waste, because I get to talk about it today. Multi-pin bases. I first became aware of these because of a talk that was actually given at Hackaday Super Conference years ago. And the guy was talking about building tubes. And he said, yeah, this is a tube base that we use. This is what you build all your elements on. This is a commercially available tube base. And then he moved on. And I said, okay, cool, commercially available. I can go buy one. Google search, you cannot find one. 35 pages of results. I'm on page 35. I'm out. There's nothing there. And so I go to the comments section, of course, of the blog post for that on Hackaday, and I find people discussing it in the comments section. Somebody has a lead on a company, precision glassware company in Rochester, New York. Maybe I can contact them, email them. They don't know what I'm talking about. I start looking around. I start trying new keywords, bouncing off of websites and sending emails to companies in China. And I did eventually find 2 suppliers that would sell me multi-pin bases. Now, what's special about these is that they kind of take the guesswork out of the glass to metal seal. Of course, you need to keep the atmospheric pressure out of your vacuum tube. Otherwise, it's not a vacuum tube. It's just a tube. And you also need to get electricity in and out of the tube, which means you need to have some sort of conductive feed through. And the way that you achieve that is by having a metal that has a very similar coefficient of thermal expansion to the glass surrounding it, so that when you heat it all up and melt the glass around the metal, and it all cools together, it stays hermetically sealed. These multi-pin bases have the pins already made, the seals already made in the glass. And so these things are called tube bases, pin bases, flat stems, button stems. They're almost impossible to buy in small quantities. They're usually made from one of 2 combinations of glass and metal. Either you're on a hard glass system, so you're using something called SHOT 8250, which is a borosilicate glass, and Kovar for the pins. Or you're using lead glass and you're using Dumet for the pins, which is another metallic alloy that specifically has this, that was created to have that same coefficient of thermal expansion. And I found these 2 suppliers. I found Moore's Glassworks in the UK, and I found Hebei Pengzhu Photoelectric Technology Company. And but they both kind of agreed on pricing. So the MOQ seems to be around 100 pieces, which is way smaller than I anticipated, honestly. But they're $10 to $20 a piece. And I don't have $2,000 laying around to just buy a bunch of glass. But I talked to the company, I talked to Moore's Glasswork in the UK, and he sent me like 15 of them as a sample. And I was very upfront with the fact that I am never going to buy 100 vacuum tube bases from him. But he was very nice to me and said, well, what we can do is we can send you a free industrial sample. And so they did. They boxed them up and sent them out. They look really nice. On a finished tube, you don't have a big ugly pinch at the bottom. You have this nice flat base with the pin sticking out that'll fit into a standard pin socket. But you need to use a compatible glass. If it's SHOT 8250, I found out the hard way, SHOT 8250 has a different coefficient of expansion than what's called a 3-3 expansion borosilicate glass, a commercial borosilicate glass that you might use for labware or like pipes and bongs or whatever it is you're making borosilicate glass items. So there is a cheap and available alternative. It turns out you can make a seal in 3-3 expansion borosilicate glass using tungsten wire. And you need to create an oxide layer on that tungsten wire by brushing it with a flame, and then you need to clean it really well, but it will seal into the glass. And I'll show you one of those seals in a little bit. Evaporable getters. These are another thing that's hard to find and impossible to buy in small quantities. There is one supplier that pops up when you Google it, and it's SAES. That's a company out of Italy, I think. But they're a global company. They ship getters all over the place, not just for vacuum tubes, but also for things like, thermoses, anything where you need to sort of maintain a vacuum. What a getter does is it sits in a vacuum environment, and it's a very reactive metal. And so it eats up any oxygen or select other gases that might evolve into the vacuum and ruin the pressure inside of the device. And so what it does is it sequesters it as a solid, right? So for instance, if you have barium, you spray a thin layer of barium inside of your vacuum tube, and now you have all of this surface area of super reactive metal, and if any oxygen molecules get in there, they will react with the barium to create barium oxide, a white powder that can't turn back into gaseous oxygen. So it turns out if you want to get these from SAES, you need to sign an NDA, basically telling you that you're not allowed to resell these to anybody, and they're really nosy about what you want to do with them. And I have talked to somebody who actually went through the process of getting samples from them, and that's fine. I mean, you could do that. I like to sign as little paperwork as I can, so I went to find a supplier in China, and I found Nanjing Huadong Electronics Vacuum Materials Company, and I got in touch, and the guy emailed me back. I said, "What's the minimum order quantity?" Like, if just, I'm a hobbyist. I explained the whole thing. I said, I'm a hobbyist. I'm in the U.S. I just want to build a few tubes. Send me a few things. I just want to see what they do. And he was like, okay, well, we can probably sell you like 20,000. Okay, that's a handful. At 38 cents a piece. And he said, I could quote you for fewer, but it would cost exactly the same. I was like, what do you mean? He said, well, I'll go get a quote. And he came back and he said, I'll sell you 1,000 of them for $4.50 a piece. Okay, so you're offering to just ship me 19,000 fewer units for the same amount of money. But he very graciously sent me a sample of 150 pieces. So I got this. Turns out, evaporable barium getters come in a Poole tab can. It's like opening a can of beans. And they're wrapped up in a little bag, and they're in the can, and the can is, I think it's probably like nitrogen sealed, and so it's like a very weird experience opening that can and crack that thing open. There's a layer of foam. You pull the foam out. There's this little baggie of little halos. And this is another thing where you don't, strictly speaking, you don't need these. You can use titanium wire. You can get titanium wire. I'm going to talk about wire here in a second. Titanium wire on Amazon, wherever you want to get it. And you can heat it up the same way as you would one of these evaporable getters. The titanium gets very hot. It does the same thing, reacts with oxygen in the tube, creates titanium oxide, titanium dioxide. I'm not actually sure how that works, but it sequesters the oxygen very effectively. And so the real reason that you get these is because they create that nice mirrored finish on the inside of the tube that you're used to seeing on commercial vacuum tubes, and it makes your whole situation look a lot more professional. The one thing that you need to do is heat them up quite hot, because what you're actually doing is physical vapor deposition. You have this thing inside of a vacuum, and then you heat it up hot enough to actually evaporate the metal. In most cases, it's sort of a mixture of barium, maybe some strontium, and some aluminum. And it sort of sprays all over the inside of the tube and condenses on the cold glass. But there are a few ways you could do that. You can try passing a current through a filament. Of course, you're not going to evaporate the entire filament, because as soon as you break it, it's done. It's a fuse. The other way to do it is to have these little ring-shaped halos that you actually heat up with an induction heater from outside the tube. And that's what I ended up doing. Another thing that I was interested in finding was cathodoluminescent phosphors. So in vacuum fluorescent displays, you get this really pretty greenish blue glow. And what that comes from is a field emission phosphor. And these phosphors aren't reactive to things like UV light and the sort of things that, as soon as I got this baggie, I was like, oh, I'm putting it under the black light. This is going to fluoresce, right? No, that's not what it's made to do. It's not what it does. It fluoresces less than table sugar. But if you bombard it with electrons, it lights up this pretty green color. And they come in various compositions, and they emit various wavelengths of light. So if you want a green one, then you get this zinc oxide zinc compound. And if you want a yellow one, maybe it's some sort of, I don't know, some other compound, right? How do you apply it? Beats me. Have not figured it out. I have a 2 gigabyte zip file full of books from the 50s and 60s on how to make tubes, and one of them has the answer in it, and I haven't found it yet. I can tell you from very limited experience that the answer is not mix it with mineral spirits and paint it on. That didn't work. I did find a supplier for these phosphors. One is Phosphor Technology Limited. Their MOQ is 100 grams. And it's only $300 for about a kilogram of their zinc oxide zinc phosphor, which as far as white powders from the internet goes, not terrible. And like all good suppliers of white powders, they sent me a free 5-gram bag. You only need these for vacuum fluorescent displays. If you want to build triodes and diodes and pentodes, you don't need to worry about any of this. And again, I have no idea how to use it. I'm just bragging about the fact that I got some. Fancy wire. Turns out 99+% purity wire, very available in all sorts of places. 316L stainless steel, titanium, tungsten, nickel. And it's because of people who build their own vape filaments. So you go on Amazon and you find all of these kits of all of this fancy wire, and it's because people wrap these extremely complicated heating elements for their vape rigs so they can blow fat clouds. So thanks, #VapeNash. Thin nickel sheet is cheap because people build battery packs and they use nickel sheet to spot weld and create voltage rails between individual 18650 cells. You can get very high purity metal wire and also more exotic wire, things like barium and molybdenum, from chemical suppliers, places like US Elements and stuff like that. And then you should also check out, I found a store called electronTubeStore.com, which I couldn't believe existed when I found it. And they sell things like Inconel, Kovar, Dumet, all of these very hard to find things. They even sell thoriated tungsten wire. That's tungsten wire that has been doped with thorium to lower the work function. You don't have to get it as hot before it starts to emit electrons. And then we need to talk about glass tubing. You can't have a vacuum tube without a tube. So, Pyrex, Cymax, these are 33 expansion borosilicate. These are the most common by far. If you are holding a thing that says it's made out of borosilicate, it's probably made out of this. It's used for test tubes and stuff. It's made for, like I said, bongs and pipes and dab rigs and all that mess. So thank you, weed. It's easy to work with because it's very resistant to thermal shock. You can heat it up with a torch, bend it, melt it, let it cool off as quick as you want in room temperature. It doesn't crack. It doesn't explode on you. And it does have a very high melting point, so that's the trade-off, is you have to get it pretty hot. A lot of the time, a propane torch alone isn't going to be quite hot enough to do what you want to do with this. A MAP gas torch gets a little bit closer. For most things, you might get away with a MAP gas torch. What you really want is oxypropane. Then there's soda lime glass. A lot of tubes were made with soda lime glass. It's very cheap. It has a very low melting point. The downside to using it in the home lab is that it has to be annealed or it will crack. You can't just heat up a piece of soda lime glass at room temperature and let it cool back down because it'll just explode. So you need a kiln or some other way to bring it down in a controlled sort of ramp. And then there's the really fancy stuff. The Schott 8250, 8270, stuff like that. This is the good shit. This is, if you want to make top-of-the-line electron devices, this is what you get. It has very well-defined mechanical and optical properties. It has a very high electrical insulation value, and it is designed specifically to have that exact same coefficient of thermal expansion as things like Kovar and molybdenum, which are pretty common feed-throughs for vacuum devices. It is hard to buy, though. I haven't yet found a retailer that just has lists of prices and tubing lengths and diameters on their site. It's one of those little red buttons that look like you could click on it and buy something, but it says call for price. And that's not a good sign. So now we know about the materials. Let's talk about some tools. This is a thing that looks safe, and it is my spot welder. The spot welder that you use has some pretty weird requirements. So you need to weld these things together. You need to weld together the metal elements of the tube because you're not going to solder them together because the filament is going to get mega hot and then everything's going to melt apart. Not to mention, most solder probably has some things in it that have a relatively low vapor pressure, and it's going to, contaminate the atmosphere inside the tube. So what you want to do is actually spot weld all of these things. Harbor Freight does sell a spot welder. It plugs into the wall. It has a big transformer in it, and you slam it down, slam the electrodes together, and it just closes the contacts on the transformer and dumps everything across the electrodes. It works great for like 16 gauge sheet metal, but it doesn't necessarily work great for like little tiny pieces of nickel wire. So probably too much juice. And a little unwieldy. I mean, the electrodes on this thing are like pretty big around. There are cheap little battery-powered terminal welders for battery building. The downsides to those is that they're a little bit on the opposite end. They don't quite have the juice that you need. And also the electrodes are configured for what's called butt welding. So you have two electrodes on the same side and you put them against the thing that you shouldn't have done that. Put those against the thing that you want to weld, and it just creates the two welds side by side. And that doesn't work very well when you have two things. You really want to pinch them together and then weld like that. Professional resistance welding machines, of course, exist. People like Dalibor Farney probably have one or two. They're very expensive, and you usually have to end up building the electrode part yourself. They just sell you a big transformer. And then I suspect that dentists and jewelers have something that they're hiding from me that would make this job easier. Some sort of little pulse welder thing that's an industry secret, and I haven't found anybody to harass about it yet, but there's got to be something there. So my advice is to just build one, but do be careful. I know that we've all heard a lot in the past couple of months about how microwave oven transformers are basically built to murder you. It's more or less true. But the nice thing about this application is that a microwave oven transformer used in this application, you actually cut the secondary out of it and you rewind it with a much larger gauge of wire and fewer turns, and so it's not actually outputting that crazy huge voltage that is the thing that's really going to come after you. It actually ends up putting out like 4 volts, but just at like an insane amount of current. So I tried to get a little fancy with mine, and I went to eBay and I bought this little spot welder control board, which is a cool board. It has like some firmware running on it. It has like a little LCD screen that shows you the pulse times and the pulse length and the space between the pulses. It has a big IGBT on it that is controlling the flow of current through the primary on your microwave oven transformer. And it basically takes a trigger signal and it runs the pulse and has a little dial and you can change the pulse time. Very cool piece of kit for $20. And you wire this thing together, and it works great for the really delicate work, but I found that what I really needed was just a melt everything pedal. And so I added a second pedal to my rig that literally just it's a solid state relay, a 40 amp solid state relay that sits across the transformer and just bypasses that IGBT and dumps as much current as my house will give the transformer through the transformer for as long as I step on the pedal. I think there's probably a compromise between these two solutions. I think ideally what you really want is not a fancy pulse welder, but you also don't want the dumbest possible solution. You want something that's like a solid state relay with like an Arduino doing some sort of timing that controls it so that you get a controlled length of pulse that you can dial in, and you're not doing what I do, which is to have a pedal on the floor and to go and try to hit the perfect pulse. You could change, there are things you could change about the circuit to lengthen the minimal length of the pulse, but it's hard to sort of make a maximum length of the pulse without getting into, you might as well just do some Arduino stuff. Glass lathe. This could be a whole thing to talk about. This is a whole other talk, maybe next year. Unlike a machine lathe or a wood lathe, which you are probably more familiar with, this thing has a few things that are different, that make it specifically built for blowing glass. It has a feed-through headstock, so you can put a piece of tubing all the way through the stock of the machine. The headstock and the tailstock rotate in sync so that your two workpieces always rotate in the same configuration. And then it's very slow, and it doesn't take a lot of axial load, the same way that like a machine lathe does, where you're pushing a knife into your workpiece and expecting it to be resilient enough. This, ideally, you're not pushing very hard on a piece of glass tubing. It's kind of in a plastic state when you're working it. The main reason that you would want to use a lathe when you're glass blowing is because as the glass heats up, it wants to sag, and if you're constantly rotating it, it keeps it sort of axially symmetrical because it's always sagging in a new direction. It also helps you because you can have two pieces that you want to seal end to end, and you can have them in the headstock and the tailstock, and they're spinning in sync. So then you can hit them with a torch and melt them down and then push them together while they're rotating and heating evenly, and you get a really nice seal. So there are commercial machines available, but they're mainly for scientific glass blowing. So there aren't a lot of really small glass lathes. They come in a variety of sizes, from sort of like large benchtop lathes to like the kind of thing that you would make a 20-liter round bottom flask on. And there are some companies that are really well known for these: Bethlehem, Lytton, Heathway, Seam. I thought that seems like a thing you could build. Which is not, I mean, that's the theme of this talk. So I came up with this idea, this thing I call the Photon open source hardware glass lathe. It uses stepper motors, so instead of using like a splined drive shaft underneath the tailstock and the headstock as you would have in sort of a traditional lathe, I just have two stepper motors that I'm going to synchronize. Do it in software, right? No machining required to build it. Everything's cut out of flat stock and then sort of like assembled IKEA style. And it's specifically built for very small work, building miniature tubes. The first one is still in progress. You can see my rendering up here of what the thing is going to look like, right? But down here is the headstock, the first V1 of the headstock, almost ready for the motors. This is the project I'm going to get back to after the conference. This is not strictly necessary. You can get a lot of work done, like I said, with a cordless drill. JD Flyback does incredible work just chucking a piece of glass into a cordless drill and clamping the trigger down so that it spins, and then sort of working on the other end of the glass. There's also a thing called a bench roller for lamp work, for glass blowing, that you can put a piece of glass tubing on it and roll it with one hand while you fire it with the other hand. And then high vacuum system. This is an extremely in-depth topic. I don't have time to get into it today. It really hurts to say that because I want immediately after this, I would like to give another 45-minute talk about this. University surplus auctions, man. I live in Wytheville, Virginia. Blacksburg is about 45 minutes away. That's where Virginia Tech is located. And they have an auction once a month, and you can buy some real dumb stuff, and they'll sell it to anybody. And so I bought a labeled surface analysis system that had two big Edwards vacuum pumps on it, as well as a turbo pump, and a whole bunch of vacuum fittings. It was all a big bench setup that I had to go and pick up with a trailer, and it was probably contaminated with who knows what. The people who last ran the machine don't even run the lab anymore, so I just took it apart with gloves on and put everything in the corner of the shop, and one of these days I'll need one of those things, and I'll have it. And the inside's probably all sprayed with awful shit, but I can clean that. I can clean that. This is one of those things where you're going to have to design your own system because there's not really an off-the-shelf solution to this that's even approachable for the hobbyist. So you're going to want to seek out people who are doing physical vapor deposition or plasma sputtering, or the homemade fuser community, nuclear fuser community, is awesome for this. They will be able to tell you which of these pumps you want to buy, because they have the experience of buying them surplus and finding out which ones survive and which ones don't, which ones are easy to run, which ones need like a very expensive and rare controller board to run, things like that. And the basics of the vacuum system are that you're not going to get away with just a mechanical pump. Some people do, actually. I will say, if you're building a vacuum tube that only needs to work for a little while and doesn't need to have a very high current throughput, then actually you can get away with using a nice two-stage mechanical pump. But ideally you would have what's called your roughing pump, which is that mechanical pump. Then you would have a high vacuum pump. And the reason you need both is because the high vacuum pump actually can't even start at atmospheric pressure. The inside of this turbomolecular pump is basically like the compression stage of a jet engine. It's a bunch of rotors and stators stacked on top of each other, and it spins at 60,000 RPM. And if you fire that thing up at atmospheric pressure, it destroys itself. Also, if it happens to get exposed to atmospheric pressure accidentally while it's running, it will destroy itself in fantastic fashion, I'm told. There's something called grenading your pump, which doesn't sound fun. What I would be aware of is a lot of inherited wisdom. It turns out large, expensive systems foster superstition because gremlins are difficult to diagnose. If it takes days and days to pump down a system and the contamination is difficult to track down, people sort of have like game day superstitions about pumping down the system, right? And they're like, well, you have to do this, 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 and this because every time I've done that, it's worked. And they've never broken a system to find out if they had to do it or not, and they wouldn't risk it because they don't own it. It's owned by a university or a commercial entity of some kind. It's not theirs to break. So just sort of keep in mind that you're going to get a lot of advice from a lot of people who really, truly do know better than you, but also believe a lot of things that aren't true. Then there's some stuff you could just buy. Induction heater. Turns out this mini magnetic induction heater on eBay, it's used for loosening bolts on like a rusty car. It costs like, it's under $200. I bought one just thinking like I could probably flash getters with that. If you can loosen rusty bolts with it, it'll flash getters. And that's true. It totally works out of the box. You just buy this thing on eBay, throw it around the tube. It gets the barium getter white hot. Works great. Torches. You can get a lot done with a MAP gas torch from Home Depot or Lowe's, whatever you're into. Eventually, you will need oxypropane. Once you get into that whole circus, you're going to start using search terms like bench burner and lamp working, and you're going to find out that National is a company that makes bench torches. You can spend as much as you want on a bench torch, and a cheap one is $600, and a nice one is $1,200, and it is just a 2-input oxypropane burner. But they're reliable, and you can find them used. Anytime that you're doing a fuel oxygen torch, you want to make sure to have good regulators and flashback arresters on everything. That's not super relevant to this talk, but anytime that I talk about torches, I want to just sort of put the basic safety stuff out there. There are a lot of arguments on forums about whether or not you need these, whether or not flashback arresters are built into certain regulator sets. Just do your research. Don't blow up the shop, not this way. And then it turns out, actually, you don't have to mess with oxygen bottles at all because you can get refurbished medical oxygen concentrators. And some of these things will output, this unit here will output 5 liters per minute of relative, 80% pure oxygen just concentrated from atmospheric air. And 5 liters per minute is enough to run a small torch. And you can gang 2 of them together and get 10 liters per minute. And that's enough to run a pretty big torch. And they're pretty expensive, but once you look at the cost of refilling an oxygen bottle and possibly recertifying it at some point, it comes out on top. I am told that most professional glassblowers do not buy oxygen bottles anymore. They run concentrators. And then, of course, glassworking tools. These are things with really fun names like reamer and smasher. Basically, it's a bunch of stuff that's made out of graphite and steel that won't stick to the glass when it's red hot. And you could buy these from like Mountain Glass or Whale Apparatus, and you can repurpose a lot of stuff sitting around your shop and use it. I found that really cheap graphite gouging electrodes, you can buy them in sets of 5 for like $15 on eBay, and those work great as just sort of a general purpose touch the hot glass tool. So finally, the tube making part. This is the sort of Hail Mary attempt at making a demo to bring to the conference. My tools are not done yet. The glass lathe doesn't work. The vacuum system is using a Harbor Freight pump as the roughing pump right now. And, I have the induction heater. That works fine. The spot welder mostly works. And I thought, I have enough. It's enough for JD Flyback. He's using a torch and a drill. So I could do this, right? It's tough. It is tough, but I did do it. So I did not expect this to work. First attempt ever making this pinch seal, and it held. So you start by taking, what this is this is an assembly of stainless steel wire, and then between the two pieces, the two forks of stainless steel wire, I've actually stretched tungsten wire. Tungsten actually itself, the metal, will not seal to borosilicate glass, but tungsten oxide will seal to the glass, and it creates a close enough bond to the metal surface that it kind of acts like a solder between them. And so what you do is you stretch your tungsten wire between these pieces of stainless steel. I'm using little strips of nickel as an interface between the stainless steel and the tungsten, because those don't like to weld together. And then you take that whole assembly, you drop it into a piece of glass, and then you heat up the glass tube and you mash it down real hard with a pair of tweezers. Before you can actually make that seal, you need to develop that oxide layer I was talking about. So you brush the tungsten wire with the flame on a torch until it turns red hot, and then you let it cool, and then I do that a couple times, just out of, again, superstition. And what you're trying to do is build up an oxide layer on the outside of the tungsten wire. But there's some loose oxide that you don't want to get in there and sort of create a pathway for air to leak through. So you need to clean that really well. So what I ended up doing was just brushing it with a torch a few times and then cleaning it with a Q-tip and some like electronics contact cleaner. I have no idea what it's made out of. It was just a can in my workshop. I think it's probably mostly like heptanes and alcohol. So like a lot of things would work in this case. Clean it with a Q-tip, put it in a piece of glass, heat up the glass, pinch the glass around the tungsten wire so that it overlaps both the stainless steel and the tungsten. So you create this one section in the glass where it's just glass touching tungsten, and there's no way that air could get through the tube. Now you have this base that has a glass hermetic seal to the metal. You can spot weld all of your elements on top of that. What I've done is I went to oshcut.com. I had them cut me out a little Jolly Wrencher out of nickel sheet. They sent me a handful of these things. They were like $2 a piece or something. I spot welded that to one of the uprights. I stretched a tungsten filament between the other two uprights. I attached that little halo on top that's the ring getter that I was talking about earlier. And then I put that whole thing inside of another glass tube, and you heat it up at this intersection here. So this top glass tube is flared so that it'll fit over that base. And then you heat this thing up and you melt the glass together. And now you have the bottom and the top section of this tube separated from each other. Then I turn it upside down and I stick that glass tubing into my vacuum system. Now what I'm doing here is reckless. I am raw dog in this turbo pump. If anything goes wrong while I'm sealing this glass, the turbo pump is going to be, best case, exposed to a lot more pressure than it's supposed to be. Worst case, a piece of glass is going to fall straight down that fitting and into the turbines that are spinning at 60,000 RPM, and then I get to find out what grenading your turbo is. I do have the O-ring that goes in between that top fitting and the bottom that has a screen in it that would kind of keep the larger pieces of glass out of the turbo, which is, if you're at the point where you're like deciding what size a piece of glass gets to go into the running turbo, you've already screwed up really bad. And then after that is the real butt-clenching part of this whole project, which is where the tube is under vacuum, and then you have to heat up the glass hot enough so that you can melt the top closed, but not so hot that it blows a bubble in on itself and explodes. And I did it. You heat it up, you twist it, give it a couple twists, you get a thin enough section that it gets real hot, you melt a little ball on the end of it, it stays in one piece, and then you get to do the fun part. It's like making a little mirror. You put the end of the coil of your induction heater over this thing, get the getter ring red hot, and you start to see the end of the tube go from clear to silvery mirrored as the barium evaporates out of the getter ring and deposits on the inside of the glass. And then you're done. So while this thing was on the vacuum rig, I was measuring 1 × 10⁻⁵ torr of pressure. That more or less is correct. haven't calibrated that gauge controller. I got it, again, used from some college. But it's in the neighborhood. It's in the right order of magnitude, right? And then who knows what the pressure in the tube is now, because after I fired that getter, hopefully it actually dropped even below that. So now I'm going to show you the tube, because I brought it with me. I was able to test the tube. I posted a video on Twitter that I actually should have added to this. Well, I couldn't have added to this presentation because it didn't get it working until a few days ago. But it works as a diode. If you set this up and you heat up the filament, it takes about, I think what I figured out is that you can pass about 120 milliwatts of current across the tube, but it takes 22 watts to run the filament. So it's not the best, it's not like the most efficient diode, but that 120 milliwatts only flows in one direction, so it's a diode. So I'm going to open up my little box here that I've been guarding with my life all weekend and pull out the little foam tube and poke the dingus end of this thing out of the end here. This is the fragile part. That's the little nipple on the end after you do the tip off. That's what's been scaring me. I'm just so afraid that it's going to break. Look, it worked. Okay. That is a homemade vacuum diode. It was supposed to be a homemade vacuum fluorescent display, but I mentioned earlier that the application process for the phosphor was opaque to me, and so I didn't know that till I powered it up. Apparently, I don't know how to do it. The silvery part on top is that barium getter. It's got a little Jolly Rancher anode in there. You can pass 120 milliwatts through it. It's you have to do that at about 60 volts DC. So it's 2 milliamps at 60 volts DC. And the filament takes about 10 volts, a couple amps to heat up hot enough to actually get that thermionic emission. But it does indeed work. And if we can find a benchtop supply around here somewhere, I can fire up the filament later if people want to see it glow. But that's kind of the whole thing. So where do we go from here? I've made one working tube, which means I'm an expert. And I can go and do whatever I want now. And this is the moonshot. This is the big idea. I want to learn how to make the things that already exist so that I can take those techniques and those tools and all that wisdom from the 30s onward and turn it into a thing that doesn't exist. This is what I call a PEMV, a planar element multi-valve. It is an integrated circuit made out of thermionic components instead of semiconductor components. What this has in it is six separate pentodes. And they're all built in a planar fashion so that you have a flat heater on the bottom, then you have a cathode, then you have some plates, and you have an anode. And you stack these things on little ceramic pins with ceramic spacers, and you enclose it, and this is all figured out. This would be an op-amp. This design that you're looking at here, it's an op-amp the size of a pack of playing cards that would get just so hot. Just really, really hot in order to work correctly. But I think you could do it, and I would love to see it happen. So that's sort of where this whole thing is heading. There are some other ideas, but this is the big one. So I think that's what I'm going to leave you with. We probably don't have time for questions. I was running pretty close on time, but if you want to catch me outside. We'll talk about tubes.